Okay, so it will be the same to us to misclassify a setosa as a Vez color or Vez color as a setosa. That's fine, okay? If that's the case, I mean, you know, because we are not in favor of any, positive class or negative class. So it will be nature to put 0.5 as a boundary. However, this is not necessarily always the case. Okay, sometimes like misclassify one way, okay, may cause much more than misclassify the other way around. Okay, for example, okay, let me use a project that I had with ITRI as an example. Okay, I used to do a project with ITRI to identify, to classify. Okay, if there's some car or motorcycle that trespass, what should I say, trespass in front of it's not MRT, it's轻轨英文怎么讲？ Monorail, you know the monorail, right? Okay, in some like in Kaohsiung, I don't know if you are from south part of Taiwan, you know, in Kaohsiung we have those type of monorail. That's really not monorail, but that's kind of like a train that is running in the city, right? Okay, and you know, we what we did is we try to use a radar to detect if some car or some motorcycle will because sometimes some vehicle will, you know, even though it's red light, they will still run through it. Okay, so I mean, before the train comes in, okay, we do the classification to identify if there's such an event. If there's such an event, the train driver will have to, you know, hit the brake to stop the train, obviously. Otherwise, it's going to be, you know, fatal traffic accident, right? So in this case, okay, if you this is going to be a binary classification, obviously, right? Okay, either there's a trespassing or there's no trespassing, right? So this is a binary classification. Okay, but in this case, misclassification, the impact will be huge. I mean, will be very different. Okay, if you incorrectly classify you know, not trespassing case into trespassing, then yeah, I mean, well, you inform the train driver to hit the brake to stop the train. Well, it's going to be inconvenient to the train driver and the people riding the train, obviously. But at least nobody gets hurt, right? But if you misclassify a trespassing into non-trespassing, then, as I say, if the train runs through that, I mean, in that situation, most likely it's going to create a fatal car accident, okay, which is you know, has a, you know, very bad, very big impact. So in this particular case, okay, misclassifying one way is much more costly than the other way around. Okay, so this misclassification does not need to be symmetrical. Okay, in the case that I mentioned, obviously it's not symmetrical. So in that case, you may want to, you know, set this value differently. Okay, you may want to set this value differently. Okay, So as you may remember from programming probability, okay, when we discussed loss function, that's different issue, but I already gave you example, okay. The example that we went through is a logistic regression, obviously, but that was a simple logistic regression in the sense that we only use one feature, right? We only use one feature, the sepal length, right? We use only the sepal length. Sepal length. And we could, basically, consider multiple logistic regression as well. I mean, the multiple logistic regression is just like a multiple linear regression, okay? It is the case when we consider, multiple features, okay, multiple features. So, okay, multiple logistic regression is about using more than one independent variables. So let's try combining the sepal length and the sepal width. Okay, sepal length and sepal width. So, and we also need to pre-process the data. Okay, so basically, like, yeah, we get the value, and then, okay, so in this case, okay, now we have two features, right? So let's consider the same situation, okay, that we want the boundary to be 0.5. In this case, okay, if you're reordering, okay, you will find that the value of x2 for which theta equal to 0.5 will be corresponding to this following equation. Okay, if you look at this one is obviously a line, right? A line. The previous one, this one is a point, right? This one is a point. So if you have like one feature, the decision boundary is going to be a point. If you have two features, the decision boundary is going to be a line. Okay, so this is very natural because you are, you are restricting this decision by a linear combination. Okay, so so if you try to extend it to n features, okay, if you try to extend it to n features, you will find that the boundary will be n minus 1 formula. Okay, n minus 1 linear formula. Okay, so it will be generally a hyperplane. Hyperplane. Okay, so actually, like if you consider like one dimension, okay, or I mean one feature, okay, its hyperplane is a point. If you consider two dimension, okay, two features, the hyperplane is going to be a line, which is which makes sense. Okay, so it's a hyperplane. Okay. So we can implement this model, okay, which looks almost identical to the simple logistic regression one. Okay, the only difference is that, okay, the beta, okay, the shape is the length of x, and which we have in this case we have two different features. Okay. And then, okay, here we use the matrix multiplication, so it's going to give you like, I mean, the linear combination of alpha plus like x beta. Okay, we will assign that to mu, and now if you look at here, okay, we still use deterministic, but now instead of calling the Thanos sigmoid function, we spell out the logistic function here, right? As I said, they are identical. I mean, if you want to use anyone, I mean, you will end up with the same thing. Okay, anyway, okay, so so you get, I mean, you apply the logistic function to get a theta. Okay, and the boundary is going to be this one. Okay, this one which is the this one. Okay, the reason to keep track of this is because eventually we want to generate we want to generate like the posterior of this boundary. Okay, so that we can generate like a 94 like a PDF for this boundary. Okay, and then okay we fit like the result and try to generate 2,000 sample. Okay, so you can plot the data and the decision boundary. It's going to be look like this. So boundary is going to be a line, something like this. Okay, and if you observe this black line is created by the average of the posterior. Okay, so that's why it has a single line. As for like why this 94% like HPD doesn't look like it has like a same width all the way. It's because like 这些东西 are not necessarily the same slope. Okay, they actually like somehow like a pivot. I know they will go through roughly the average of the x and the y. Okay, so with a slightly different slope, so that's why it creates this kind of like a it's wider on two ends, narrower on at the center. Okay, and you can see that this result classify these two classes pretty well, right? It classifies these two classes pretty. There's perhaps a little bit of you may misclassify these few points because they are actually very close to already inside the boundary of the decision boundary. They are already inside the decision boundary, so they may be misclassified. But at least, you can tell that this classification it works for most of the cases, right? Okay. So I think I already explained it. So we must be careful when we try to interpret the beta coefficient of a logistic equation. Okay, interpretation is not as straightforward as the linear model. Okay, which we look in linear regression models. Why? Because the logistic the inverse link function has a long linearity. That we need to take into account. What do we mean by this? Here, you see, this is the result of like a logistic function, right? So this logistic function, is nonlinear, in the sense that when your feature is getting close to the center, your result change faster than when your feature value is like near the two ends. So the change happen quickly at the center because obviously you can see the slope in the center is much steeper than the slope at the two ends. So yeah, when you try to explain like the beta impact of the beta, it's because the impact is not linear. Because of the logistic function. We use logistic function inverse link function. So yeah, it's more difficult to explain it. Okay, so if beta is positive, increasing x will increase this p probability that of the positive class by some amount, but we cannot specify that amount very well. Okay, the amount is not a linear function of x. Okay, instead it depends nonlinearly on the value of x. Okay. It depends where you are talking about that x. If it's closer to the center, the change is going to be bigger. But if it's like near two ends, the change is going to be not that much. So you can visualize this fact. I already showed you that slide 18, okay, which shows that logistic function. Okay, so instead of a line with a constant slope, we have a S-shaped line with a slope that changes as the function of x. So a little bit of algebra can give us some further insight into how much p of y equal to just the probability of the positive class changes with beta. So yeah. So this is the algebra that I was talking about. Okay. So we have this theta equal to logistic alpha plus x beta. So we know we can apply the inverse of logistic. The inverse of logistic. Okay. So if you apply the inverse of logistic, the inverse of logistic is called logit. Okay, logit is defined like this: log, okay, z over 1 minus z. Okay. So if you apply this logit function on two ends, okay, on the left hand side is the logit theta, obviously. On the right hand side, because the inverse function and the function they cancel out each other, so it's going to end up with alpha plus x beta. Okay, and then you can write the left hand side into the original form of logit function. Okay, so this 1 minus z, okay, is 1 minus theta. Remember what the theta is. Theta is the probability of the positive class, right? And now we are talking about the binary classification, right? So 1 minus theta is the probability of negative class, right? Right? Okay, if theta is probability of positive class, 1 minus theta, because we are talking about binary classification, so 1 minus theta is the probability of negative class. So interestingly, okay, alpha plus x beta will be the log of probability of positive class divided by probability of negative class. Okay. In other words, okay, we in mathematics, okay, we call this value. This is theta divided by 1 minus theta. Okay, remember theta is the probability of positive class, right? And so we can write it like this. So probability of positive class divided by probability of negative class. Okay, this quantity is known as the odds. Okay, mathematically, okay, where does this, you guys probably have learned like a probability from, I'm not sure, like from high school or at least like, or like in college, you learn probability, but you may not heard of these odds. I'm not sure if you heard of this, okay? But anyway, these odds, okay, in mathematics, where does this concept gets used? It gets used the most in the gambling situation. Okay? For example, okay, the odds of success are defined as the ratio of the probability of success over the probability of not success. So for example, the probability of getting 2 by rolling a fair die. okay? Because the probability of getting 2 is 1 over 6, right? And the probability of not getting 2 is 5 over 6, right? So if you divide these two amounts, you get 0.2. So that's the odds of your, or one favorable event to 5 favorable events. So, I mean, if you like to go to gambling, like a casino or somewhere, this odds is a very convenient way to calculate the chance of winning, and which is used actually very often. But other than the gambling situation, it actually doesn't get used that often. Okay, but anyway, because once we can write it like this, it means what? In a logistic regression, the beta coefficient encodes the increase in log odds unit by unit increase of the x variables. So when the x variable increase by 1 unit, okay, when the right-hand side increase by 1 unit, the log result of your odds increase by, by 1 unit as well. So that's why we call it the increase in log odds. Okay. Yeah. So yeah, I think let's take a 10 minutes break. When we come back, let's continue the discussion. Okay.